Right. Hello, and welcome to our webinar, Week 9. I am Noah Brenner, as I have been all of these past weeks. Welcome to here. Let us do some more looking at Spark and data lakes in general. So we dived in a bit a couple weeks ago. Last week we looked at Git. That was a lot of stuff there. Happy to answer any questions if any of that came up for you there. So let's dig into some more things. I'm going to also show some examples, and most of these examples are just some of the content directly from the course, exactly the same code examples. I just want to talk about some aspects of them and pick them apart a little bit so we understand really what's going on. It's always better to know what we're doing and why rather than just the what. Not as useful. So I'm going to share my screen here and we'll get started on that. I'm going to look at this window. So we're first going to talk about functional programming versus object-oriented programming. Both are good things. This isn't about one being better than the other. And the cool thing is that Spark has that's a different thing. Sorry, Spark uses a functional programming approach, and that is particularly useful. Because functional programming is a little easier to reason about once you're introduced to it, because things are predictable, because nothing is going to change. When you run a pure function, you will always get the same result. You're not going to get a different result based on the environment or the number of times you have run that function or any other things like that. But that means a few other things as well. So that seems obvious, of course. Yeah, if I run a function, I want to get a result. But a lot of things that we do think of as functions might have other results. Even something as writing a file. If you're running that function, it's not a pure function. It wrote a file. It had a side effect. It affected something other than just the return value. So here's an example in Spark. We created our log data frame here, Spark read CSV, some file name that I didn't specify. And here we can do something with that. Here we did log.filter, and we're filtering where the page equals next song. That's great. This was important, though, that I assigned this back to log. If I had done this, not that, that was too much, this much, this would not have accomplished anything because a pure function is not allowed to change state. So log would still have the same value at this point, even though we're calling a function on it. This returns something, but log down here would mean exactly the same thing as log meant up here. It would not have this filter applied. And so in order to actually apply that filter, in effect, I need to reassign it to either a new value, or in this case, I reassigned it to the same variable name that it had before, but now this is a new value, a different one than it was before, or than it is right here. So that's the one potentially surprising thing if you haven't used a bunch of functional programming that could catch you, is you have to remember that you do need to reassign that if you're making a change here. And then, of course, here's another question for you if you've been reading up on how all this works in with the lazy evaluation that Spark uses. At this moment, right here, aside from reading the data from the log file here, have we actually run any processing? Have we done any processing or filtering of the data as of this line right here? What do you say? Yay or nay? In Spark, it is going to be nay. We have not done anything here to actually process the data or to filter that song, because we want to do our work efficiently, and we might build up this work piece by piece. So we're not actually going to evaluate it right now. It's lazy evaluation. We're not going to evaluate anything until we actually do something like collect or show. Because we might have various transformations here. And if we were to actually run each individual transformation in that functional world, we would come up with a lot of duplications of the data. We would use a lot of memory because we made an entire new set of the in memory of the data here. And then if we did another filter or some other operation, it would be yet another full set. And so by doing that lazy evaluation, we get some chance to avoid some extra work because we might be able to not do some of the later work or not do some of the earlier work, depending on how all those pieces are working together. That's that DAG that we talked about actually not last time, that was 2 weeks ago, 2 times ago, for the directed acyclic graph, where Spark makes a plan for how to make those queries that you're specifying efficiently without doing extra work. So we're contrasting that with an object-oriented programming. So a good example, and again, taken right from the course content, here is matplotlib. And so here, look what we're doing. We're saying we're going to create a scatter chart here. Going to give it, here's our x-axis placed by hour, hour and then the count. But so now we have something that exists. We have that plot. And then this plot, we're going to change the x limit and the y limit and add a label and add another label. And so you see that we're not saving these things again, and they're changing the state. They're changing something, some data object in memory on your computer exists that is that plot, and we're not creating a new one. We are modifying the existing one by setting this limit right here. So we are changing state, and that could be surprising if this happened somewhere else. If this happened up here, and then we had just a whole bunch of code. Hey, why am I not seeing all the data? Why is my x limit only going from -1 to 24? So it is useful, in certain senses here that can be less verbose. We're not having to reassign a value, but it also can be unpredictable, hard to follow there. Okay, no worries on coming in late. They happen. It's all recorded, so that's why we're recording it. Yeah, so just there's that idea that there's nothing wrong with object-oriented things, and it's a way to sort of contain something and to be able to think of making a modification to an object, where you have a class, and now I have a puppy as an instance of that class, and I can do various things with it. But when we're doing data processing, it can be a lot more intuitive to have data in, data out, always be the same, always predictable, not affected by anything else. So there we have it. It's functional versus object-oriented. 2 different approaches to programming. It's not that one is better than the other. It's that they both have different applications where they are perhaps more or less valuable. So that's one contrasting thing. That was functional versus object-oriented. Now we're going to look at imperative versus declarative. These are somewhat subjective, and they are just different. It might be more useful to think of imperative and declarative as a spectrum than as 2 entirely distinct things. But here, Spark gives us, well, at least actually does another third, but mainly these 2 interfaces, 2 ways that we can work with the data. And we could absolutely accurately describe one as more imperative and one as more declarative. So imperative is that one where we are specifying exactly the steps that we want to take. What are the exact instructions to accomplish a task? Whereas declarative is describing what the result is that we want, And so the example here is, here's our imperative example. So I'm going to come back to the UDF in just a minute here. So we have our log. We're assuming that already exists. That's a Spark data frame. We're adding a column called isTargetUser using our user-defined function up here that I'll talk about in a minute. We're going to group the things by the page. We're going to sum the column isTargetUser. We're going to filter out that sum column, so for the things that are 0, or wherever that sum is 0, and then show the result. And actually, you can see that that's a lot of the same syntax as SQL, but it's not in the same order as SQL. So with column isn't that, but group by, sum, filter, let me guess that would be where would be filter in that case. And we actually can use where here instead of filter. That's an alias. But here's exactly the same query, but in SQL. Here we're saying to select distinct page, so only one of each one, from logs. That's our table that we created right here, where the page is not in this other list, and we're doing an internal, another query here, select distinct page from logs where the user ID equals blank, because this is just one of the examples of from one of the course content little like quiz things. These are a couple of examples here. So this is accomplishing the same thing, but we can also say here we're in SQL, we're not really going into detail about how we're going to accomplish this. We're saying what we want. What I want is a unique page. I want you to, out of the log table where the page isn't in this list. So that's not in the order that we do it. If we were to do it in the order, well, we first have to say, where are we getting it from? And, getting the page, making sure that it's distinct, making sure that it's not in this list. We're kind of hopping around. But here we get to describe what the data is that we want. Whereas here we're saying each individual step, add this column, group by this page, add up this thing, filter out those things, show them, and it is in that order. And if we were to change that order, it might not work the same way. Although I am going to, again, go back and say that I'm going to think of this imperative and declarative as being a spectrum rather than an explicit is or is not. Because we could also go much deeper into what does it mean to add this column. We're not going into, setting aside that memory, in there. We're not telling it where to store that in memory. We're not having to go into the implementation of what group by means. We're not having to iterate through each row and say, oh, this has the same value for the page column as that one, so let's group those together. We're not needing to go into that detail, and obviously all of those steps have to happen, but we're not going to that level of detail. So this is more imperative than this is, but there exists something that is more imperative than this. That's you get farther and farther down until you get to the compiler language, the actual machine code, and we're not going to go all the way down to machine code. But that's the idea there. And I like that we get to still use SQL, and both of these will also be evaluated the same way. No matter which one of these we use, Spark will be making its own, making its DAG, making its good plan for how to efficiently execute this query to get the data that we want. So there isn't, frequently there isn't a meaningful difference between which way we want to do this. It's just whichever way we're more comfortable and familiar with. It's probably a good idea to be consistent. There are a number of things that you can use one interface for or another interface for Spark, but both so that you get to be familiar with it. It's a great idea to pick one and get really comfortable with that, but also for the sake of maintaining it, for collaborating, for having someone else read your code, it's going to be a whole lot easier for them to see consistent interfaces, to say this is the code style for this project of how we're going to accomplish this task. If we're switching back and forth, it gets a little bit muddy, gets a little less consistent and harder to manage and parse and figure out why you chose to use one method in one place and a different method in the other place. So I do not think that there is a better one. It's just up to you which one you feel like you want to use, that you like here. Okay, so now let's go a little tangent, not tangent, we're just going to go to the details of what I happen to include here. So here we have a user-defined function. So clearly, UDF is something we needed to import from Spark. We're just not looking at that right now, right here. We do need to do it here because it's not just an ordinary function. It needs to be a function that Spark knows how to deal with, and that's why we're passing it to here. We've given it a lambda function in here. That's handy because that means we get to just define the function right in line in one spot here. We're getting the information about what that function does because we've given it a name here, so hopefully that's a descriptive name so that we know what it means. But of course, we could have done this another way. We could have said, we could have defined even a regular sort of function that I'm going to call it something else. I'm going to call it is target user, but I put an underscore so we can distinguish it. So that's going to take one parameter, and that's going to be the user ID, and then we can return 1 if user ID there. Else 0. And for that matter, I could even break that out into a more standard if-else statement. And then we could have said, now is target user equals UDF target. I haven't finished the thing yet, but effectively we could do the same thing. It would mean exactly the same thing. So here's our function reference to the function name that we defined here. But we can just do it all in line and use a lambda function. That's nice. A very, very important thing to remember in Spark when using user-defined functions is that by default, if you don't specify anything else, the output of whatever your user-defined function returns will be assumed to be a string. Doesn't matter what you actually returned. Here we returned an integer, either way. We returned an integer, but that doesn't matter to Spark. We still need to define it in the UTF, so it will, in this instance on this line that I'm here, Spark will interpret it as a string 1 or 0 because that is the default. So if we wanted to interpret it as something other than a string, we have to tell it that. And so that's why up here we're saying integer type as the second argument to the UDF function. So here we can do the same, integer type. And so now whatever our function returns will be interpreted as an integer. That is an important thing to always think about whenever you're using a UDF. I think this probably also makes sense to enforce some consistency because Spark is using that functional programming idea. One of the other aspects that it's going to probably be using here is that it also needs to always be the same type, because in Python we could have done this. We could have returned the string 1 here in this case and the integer 0 in this other case. That would be a bad idea. That would be bad form. We shouldn't do that anyway, but the point is we can. But that's not going to work terribly well for Spark because it needs the data types to be consistent within that column. And so it is enforcing that by making us define what specific type we want that user-defined function to return. Okay. So then in our declarative place over here when we're using Spark SQL, we do have one step before we can do this, because notice up here, we were making our query based off of the Spark data frame, the log.with column and all that here. But with our Spark SQL, we're actually doing spark.sql. So not our data frame.sql, but spark.sql. So how is Spark going to know what data frame we are referring to when we're doing this? We have to register it. So here's our log, here's our data frame, our Spark data frame. And we're going to do create or replace temp view, temporary view, and we're going to name it logs. So this effectively makes Spark behave as if there is a SQL database and a SQL table in that database named logs. And that's why we can do select from logs here. We needed to set this up, otherwise that wouldn't work. And you can see that it's create or replace. So if we then down farther changed what log was, rebounded, or changed what value we wanted to put in our logs table, we could do that again down farther. And having that separate allows for things also like joins, because it might not just be on one, so we can do a join here on multiple tables, multiple data frames that we have created a temporary view to be a table of. Okay, good. Any questions on any of this so far before we go on? All right, feel free to let me know if there is. So we're going to go on. We're going to look at Spark collections. And what do I do? Actually, yeah. Do I have these here yet? Yeah, we do. Yeah, we have the examples. That'll be good. Okay. So here are some different types of collection types. So in our user-defined function, I'm going to go back to the last one again. Here we defined an integer type, but there are other types. We could do a double type, we could do a string type, we could do all sorts of different types. But those are the single unit types. But then we also have collection types that can contain other types. The main one that we're going to encounter, even if we don't see it by name, is the struct type. And that's the type that gets essentially mapped to what we end up seeing as columns, or it's something that is very easy to think of in the same way as a relational database, as a SQL database. So struct type is, when we define it here as a list, when we're defining a schema manually in this particular example. And a struct type is going to have, a label and a type that goes in that column. So here's a struct field that is inside our struct type. So here's one called payment ID, and what this means is this is a column called payment ID, and the data in that column is an integer type. That's what we're defining here. And the integer type, here's our double type, here's a date type in this case. So this is the thing where we don't actually have to define our schema manually. It can be inferred by Spark. That's really cool. That's like we can just dive in without even having to go through and write the equivalent of our create table SQL query. But we can. It's going to be useful to have a record of it. I'm not certain, but I think I may have heard that there are times when it can be faster. It can load the data faster here, since it doesn't have to do the work to figure out to make the good guesses of what data types those might be. You could just give it to it. That's neither here nor there. It's an option, and it's particularly useful if Spark isn't making good guesses. Very frequently we run into that with a date type. That might be a timestamp or something, and it will either see it as a string if it's in that type of format, or it might see it as an integer, even if it's another type of timestamp. So there's a way we can do that. Here we're reading from a CSV file. That's where it is, and we're defining our schema, saying it's that payment schema we defined up there. Also going to say, In this particular example, because this is just copied from one of the examples we had in the course material, we had our separator was actually a semicolon rather than a comma. Find that. And what to do when it doesn't line up with the structure that we define. So there's the thing. When we infer the schema, we're not going to lose any data because we can always just go to a more generic type of information. All of these values were something that we could call an integer. Oh, but this last one wasn't. It was some other thing. It had a letter in it or something. Okay, well, we'll just call that string then, is what Spark can do. But here, if we're defining the schema, everything in that column does have to be what we defined, the data type up here. So what do we do if it doesn't? In this case, we drop malformed or replace it with null, various things. You'll see that. So here's our schema. Again, this will be familiar. This is the normal thing. This is what we're used to seeing. So here's our root, and in there we see payment ID, it's an integer, customer ID, it's integer. And here are what we can think of as our columns if we are in SQL mode in our brains, and whether or not it's nullable over there too. This should not be a surprise to you. This is the first thing we see. This is the usual thing we see. But, and here's again the really cool thing, Spark can represent nested data structures. It doesn't have to just be as simple as this. For that matter, you can have another struct inside here. One of these values could be a struct, or the types of them. So let's go to another one. Here's a MapType. We can skip over, a lot of this is just implementation detail. We're doing some regular expressions and stuff. But over here we have this. That's probably familiar. There's our map. There's our object or our hash or whatever programming language we're in might have slightly different terms for it. But that's our idea. We have a key and we have a value. That's what we have. It's not ordered. So we have to, obviously we're defining it in some order or other, but internally the data structure does not have any inherent order. And we can see that it's in these curly braces rather than the square brackets. So yeah. So we're parsing this for UDF to pandas. Print. So here we're going to print the schema. And here, what did we do? Yes. So this is important. All of what we were doing here, we were defining another user-defined function. Here we're using a decorator. You're going to go next week. We're going to talk about a number of Python features. We're starting to encounter some other advanced, but some more than just the basic Python features. So next week we're going to go over some of those, so we're familiar with them. At the moment, don't worry about this. This is the same thing as just passing this function to the user-defined function thing here. And here we're defining what the output type is going to be. It's going to be a map type instead of a struct type that we did before. And here we have two things we need to define because a map maps something to something else. So the map keys are going to be strings, and the map values are also going to be strings. We had to say that separately because that is not inherent. They could have been otherwise, or they could have been different. But here we see that all of our keys are strings, and all of our values are strings. And that includes this one here. Notice up here we said size equals 0. 0 is an integer. But that doesn't matter. Since we've mapped this in Spark to say string type, that will be interpreted as the string 0. Every single one of these will be. So here, let's look at the schema. Here we have our root value. I think that was something else. That was our original value. We're not worried about that. What we just created was parsed. Value was the source parser we created. And this is a map. That's the type here. And that map has key string and value string. You might notice that there are only two things. Here's a key and a value. What we actually gave it here was a whole bunch of different values. What's that? 1, 2, 3, 4, 5, 6, 7, 8, 9. That was 9 different keys we gave. But it's only showing key and value. That's another aspect to this. A map does not require any particular set or number of values. It could have zero keys and values. It could have many keys and values. It doesn't have to have the same key and value set in one place as it does in another place. Take what you will. Sometimes that's a good thing, sometimes that's a bad thing, sometimes that's just what you have in your data set, what does that mean? But here we're really defining the type of data, the type of mapping that we have. We don't have a guarantee that it's always the same number of elements of keys and value pairs that we have in there. And then later in this example, that when you get through there in the course material, we end up turning back into a struct so that we do get to see something more like a column. So we're kind of getting that in a mapping. A map is different from a struct. So here we have an array type. In the examples, we never directly used an array type. We kind of implicitly used an array type. So functions, so this is Spark SQL functions, splits it into an array type. So that's what we're doing right here. We took the title and we're splitting it on strings there. That's spaces, yeah. Splitting. So essentially, this function right here is returning a Spark array. An array is a series that is ordered of values, and that series all must be the same type. So you can see some comparisons between both of those. It's similar to a struct in that a struct has consistent values. Always has consistent values for those columns. Same thing for the map. An array doesn't necessarily have a set size. This could be any number of elements in that array, but every element must be the same type, which is different from a struct because each column could have a different type. But in an array, it's all got to be the same. In this case, it's a string, could be other things. So there's our implicit array type. And then we immediately don't get the array type anymore because then we use the explode function, which turns each element in that array into its own row in a struct type. So we kind of used a bunch of these here. So we temporarily created this array, turned it into a struct, and so now we can see this here. So in that array that we had for a minute, to was an element, the was an element, of was an element, in was an element. And now we turned each of those elements into their own row. Here we just have the numbers for the rows, and here we did a count because that's what we did here, because we did group by word and then count, and then order by count descending. So those are our main types that we have there. That's what we got. So again, that review of StructType is the one that we'll probably see the most. It's maybe the one that's most intuitive to us since we've been working with SQL. That is a set of, in our case, columns. So what we can really say is the root here, the type of the root in this case is a struct type. And that struct type is made of these elements. Payment ID, customer ID, so all of these, it has a set number of them, a specific number of them. We can't have more or fewer. Every row has to have all of these columns. It could have null as a value, but it still has to have a value there. And each of those columns can have a different data type. Here's an integer, here's a double, here's a date. Map can have any number of values, but every single value must be of the same type. Map must map one consistent type to another consistent type. Both of these had pairs, so they had a label and a value. In a way, we can think of both of them as having a key and a value. An array does not have a key, it only has values. I guess the array would be the index. And all of those elements must be of the same type. And so we can use those same things. We can define, we can define our schema that way too. and these can be nested as much as we want. And so that makes it a much more dynamic type of interface and be able to represent a lot more complex data than we could, at least very easily, with simple SQL, where we just have that flat structure. We have multiple tables, but we don't have really that concept of nested structures. And come up with ways to represent them, but then we are forcing a data structure into another one rather than representing how it might want to be naturally. Interrupt me if you have questions, otherwise I will go on. So this is something I'm actually not going to go into big detail. Just a little overview. These are some things that were presented in the course material, and they were presented great, and I just wanted to make sure I catch some potential confusion, since there was something that looked like it might line up but actually doesn't. So these are some, the top section and the bottom section are two different things we're going to look at. First one is this top little table here. Again, it's a table I just made from what they'd shown in the course content there. So this is 3 different ways that we could implement a data lake using Spark and using AWS. Of course, remember, that's not the only options. There are other providers. There are other tools than Spark to accomplish this, but this is the example that we're looking at. So what type of storage, what type of processing, and then here are 2 different ways of implementing that combination of storage and processing. We do the AWS managed version or the vendor managed version. So if we are saying we're going to use HDFS, so that's, remember that Hadoop something or other file system, that's, I don't know why that word just left me, and processing with Spark. Well, we could, so that's, remember HDFS, that's the one where it's distributed. There it is, a distributed file system. This is the original model. This is the one that we looked at when we were introduced to Spark and why this exists and how this exists. And this may be the most efficient in terms of the processing. It may, depending on what implementation you're using, it may not be the most cost efficient, and that's something to decide on each given project, just because of paying for the resources. So with this one, with HDFS, we're saying we have a bunch of nodes. They can all be commodity hardware. Data is duplicated, and the same nodes are storing the data as are processing the data. So all of that commodity hardware, all those computers hooked up to each other, they all carry some storage, and they're all going to be doing processing on that storage, on the data that is specifically stored on them. And that's why it gets to be very efficient, because we're not having to transfer data around all over the place. Once it's there, once it lives there, all of it is processed immediately from the same computer where it's living. So we're not having to go across the network, which, as you remember from before, is the slowest part of that stack, the slowest element of the hardware to transfer data around. Data processing in Spark, that's what we're doing. So AWS managed, we could use AWS EMR, Elastic MapReduce. So that can scale up and down and be very useful. That's great. So HDFS plus Spark. So we're using EMR, so we're not having to implement this directly ourselves. It gives us that interface to work with. Vendor managed, but still through AWS, we could get EC2 machines, and we could install a vendor solution that could be our own or one that we purchase from somewhere else, and use that to manually go do the process ourselves to load the data onto those EC2 machines in a HDFS cluster and manage them directly that way rather than having it set up for us. Second version is data on S3, still using Spark. Again, we can use Elastic MapReduce with Spark only, so it's not including any storage here because the storage is all on S3. And same deal, we could implement that ourselves. We could get EC2 machines without any storage, load it in, load it out. And then the last one is S3 and serverless, and that'll be AWS Athena we were looking at, or serverless in some vendor solution. So serverless is, where you're in AWS, you'd be using sort of the Lambda service, AWS Lambda, and that's that abstraction. I think we covered a time or two ago, where instead of even thinking about an EC2 machine, so thinking about a virtual machine, we're not even we're abstracting even farther than that, and we're just saying, here's a function to run. Not thinking about where that function is installed, how many machines it's installed on, where those machines are. Just here is a function, and it will and AWS will manage scaling up and scaling down to manage that demand. So you can have multiple instances of that running. It's really just charging by the by runtime and by number of calls. So those are our 3 models for doing this. So then the confusion is there are also 3 examples that we looked at, but these 3 examples do not actually map to these 3 different versions. We in the walkthrough of those examples we didn't get an example of this first one at all, but that kind of makes sense. That's the most intuitive one. That's that's how that works. And the difference is that we're dealing with HDFS, which is great, but also potentially more expensive, because the other side of that is, since the same machines are storing the data and are processing the data, when you're done processing the data for right now, you can't just shut those machines off, because those machines are also storing your data. And so you will lose that data if you shut them down and let them be reallocated to someone else who needs an EC2 machine at the moment. So that could be very good if it's on premises, or if you do need it 24/7 and you have that kind of load, or it depends on your implementation. But if you don't, if you're only going to do little fits and starts, that's going to be a lot more expensive, because paying for compute resources is a lot more expensive than paying for storage resources. S3 is impressively cheap, just storing the data. So that's kind of why we didn't end up looking at that one this time. So over here we have, these were basically the 3 examples. One was we loaded the data locally from S3, but we're loading it to whatever our local computer is that we're running. So in this case, that's the VM that's running the Jupyter Notebook that we're running. And then we examine the data. Essentially, that is version 2 here. That's S3 and Spark, and we just never saved the data. We examined it, but we didn't save the output of our data. We just exported it. The second walkthrough example that we did, we used, again, EMR. Well, actually, this first one, we didn't use EMR. We did it ourselves, but same idea. But here's used EMR in a Jupyter-based notebook that's hosted. So that's pretty cool. And you see that we get to set this up on AWS. We get to use AWS EMR. And there are multiple ways to do this, but one of them is to use essentially a notebook that is Jupyter-based. It will look basically identical to the workspaces we've been using. You just don't even have to do some of the setup at the beginning. You don't need to create the Spark session. You'll already have Spark bound to that session. You can straight up use Spark immediately right from there, or you can submit full scripts. So the second version is this second version here, and the first one is kind of part of it, but doing it locally rather than using EMR at all. And the third one, use Athena, does map to the third one here. So that's where it's Athena is well, Athena and our other service that again is slipping my mind, that we're using to collect the data from wherever it is that we want, put it into tables, mapped as tables, and then we can write SQL queries and save them. So we can have saved SQL queries, we can run one we want. That's a pretty cool solution too. That's very much cloud native, and it's built off of using those lambdas, whereas EMR is built off of EC2 machines. So the way of scaling that is different. So that means that when you're using EMR, you need to define what class of EC2 machines you want and how many of them. With Athena, you don't. You're just saying, here's what I want to do, and it will take care of the scaling of the various things. Okay. Yeah, I guess the Jupyter-based notebook or something like that. This is closer to what we'll be doing. We won't be using EMR for the project itself. We will be doing more of this load locally thing, but then we will be saving the data back to S3. I believe we'll be loading the data from an S3 bucket that Udacity owns, but then you'll be saving the data to a bucket that you own, to a different bucket, because obviously you don't have write access to Udacity's bucket. So that's how that project will be going. I do believe that is mainly what I had there. So this would be a great time for questions. One person ran into something about globs, so I'm happy to talk about that. Or if you had any other questions about Git, since we did a lot of that last time, and we even went over a lot of information there. So, does anyone have any questions? All right.
No questions, I said. I'm still a lot behind on the coursework, so just listening in. I'll probably listen to this again and then come back with questions some other time.
Sounds great. And actually, I realized sometime last week or the week before, I took a look at sort of the plan of what various subjects we're going over in the webinars, and I realized that I actually did get a tiny bit ahead of myself. So I am ahead, you are not behind, it'll all be fine. And so that's why spacing these things out a little bit more. And so again, next week, we'll be working on some more generic tools, some more things about Python that are not specific to the projects. And the following week, we'll finish up with some hints and tips and stuff for finishing up this specific data lakes project.
I have a suggestion, since this is the only group that comes to this every week, and maybe one or two people more. Can we have next session as a Q&A session with the course content that has been covered until today?
Sorry, one second. I'm having trouble hearing you. I think there's a fan going on in the other room. I'm going to cover up my door here. I wonder if you could get a little closer to the microphone. Sorry, I missed your question there.
Is it good now?
Yes.
I was hoping, since we are ahead, why not have next week's session as a Q&A session? And that's a question not just for you, for everyone present here in this webinar.
Absolutely. I think that would be a great idea. And that's actually sort of my first idea for doing that. So I think that since I saw a number of those Python features things, I think I do want to go over some of those, but I don't think that will take the whole time, and it would be a great time to try to have the biggest focus be on that being a question and answer session. I like that idea a lot. Yeah.
Okay.
I'm also good with that idea, Noah. This is Premjit here. Like
Great.
what Abba said, I think what we could probably do is also post some questions into our Slack channel so that there's a little context and all of us see a shared context. And then we come together in the webinar to listen to your response to the questions and interact.
Yeah, that would be great. And that would also mean that anyone who, just the schedule didn't allow to actually get to the webinar can still ask those questions, and we can still cover that in the webinar and still have that value to everybody. I like that idea a lot. I will definitely do that. Do you have any suggestion about whether I should announce that that's what we're going to do and call for questions right away, like later today or tomorrow, or do you think maybe wait till a little closer, maybe like wait till Monday or something of next week?
I was thinking more like Monday, because I know even I'm a little behind. I've just started working on the project now.
Mm-hmm.
So yeah, I was thinking more like Monday is a good time.
Great. Yeah, so I will announce on Monday that our next webinar that later that week will be a primarily that Q&A, and that'll be a great thing to do. And so that you can ask questions right there in the channel to both give me a heads up on them, but also to be able to ask them even if you can't make it to the webinar.
Yeah.
That's great. Let's definitely do that.
Thank you. Thank you so much.
Absolutely. Thank you. Appreciate that. Yeah, I think that's mostly what we got. Yeah, that is all I have. We actually finished 7 minutes early instead of 15 minutes late. Good go us. Thank you, everybody. One more round of any other questions for right now before we head out?
None right now, Noah. This is helpful. We'll catch up next time after I do a little bit of groundwork. I haven't really been keeping up with the lessons.
That's okay. Life does what life does. Thank you so much, everybody, for being here, and I will see you next week. And I look forward to doing that Q&A.
Yep.
See you then.
Thank you, Noah.
Bye.